Hello and welcome to part 2 of homework 4. And so in this video I'm going to be finding numerical values for the changing of height in each tank and the changing of the flow rates into each tank. And this is using the model that we found or that we defined in the previous video. And so these equations we also derived in the previous video, and we just have equations for the flow rates at an initial steady state, the changing of volume with time, the changing of height with time, that's the changing of height of the liquids in each tank, and then the cross-sectional area as a function of time for the liquids in each tank. So I'm not going to be going over the derivation of those, however in the previous video I derived them, and in this video I'll just use them. And so in this video we are going to try and find how the height of our tanks, or the liquid in our tanks, change with time after the inlet flows to tanks 1 and 2 change after certain time instances. So after 100 seconds, we have the inlet flow to tank 1 changing to 80% its original value. And then after 200 seconds, we have the inlet flow to tank 2 changing to 250% of its original value. And so to do this, we are going to make use of some of these tools that I've brought in, and then I've also just defined a default template for a plot. We're going to eventually make a plot of how the flow rates into our tanks change with time, and then for that same time interval we will show how the heights of our tanks are changing. And so I've gone ahead and listed out some of the given information here. So we have a specific time, or a final time I suppose, and basically this is just some arbitrary value. It could be any large number, but basically a length of time that we can evaluate all of our equations through. And so it's really just got to be greater than 300 or 400 to make our plots eventually accurately represent what's going on. We have the radii of our first and second tank as being 4 and 2 meters respectively. The cross-sectional areas of the pipes between 1 and 2, tank 1 and 2, and then the pipe leaving tank 2, they have an equal cross-sectional area, 0.2 meters squared. We have the initial heights of the liquids in each tank. The initial height of the first tank's liquid is 5 meters, and then for the second tank it's 3 meters. And then for, as you can see, we have a square root of 2g term pop up a couple times. I just basically assigned it a value so I don't have to type in that whole thing every time we need to use it. And so of course we need to start off by finding the initial flow rates, because of course we need to know the initial flow rate to find what 80% of the initial flow rate is, and of course the same for the second flow, or the second inlet. So we can make use of the initial steady state equations that we've defined over here. And of course we can see that the flow rate between tanks 1 and 2 and the flow rate leaving tank 2 are both only dependent on the cross-sectional areas of our pipes and the heights of the liquid in each tank. We're given all that information, and so we can easily find the flow rate, or all of the flow rates in our initial steady state system. So the initial flow rate between tanks 1 and 2 is going to be the cross-sectional area of the pipe between tanks 1 and 2 times the sine of the difference between our initial heights times the square root of 2g times the square root of the absolute value of the differences between our initial heights. And then the initial flow leaving tank 2 is going to be equal to the cross-sectional area of the pipe after tank 2 times the times square root of 2g times the square root of the height of the initial height of the liquid in our second tank. And then the flow of the flow entering tank 1 initially has to be equal to the flow leaving tank 1 initially, because we have an initial steady state. And so the flow coming into tank 1 initially has to be equal to the initial flow between tanks 1 and 2. And then the flow leaving tank 2, or sorry, entering tank 2 has to be equal to, as we can see from this equation, in the initial steady state system, the initial flow entering tank 2 must be equal to the difference between the flow leaving tank 2 and the flow entering tank 2 from tank 1 initially. And so the flow rate entering tank 2 is going to be equal to the flow rate initially is going to be equal to the flow initially leaving tank 2 minus the flow from tanks 1 to 2 initially. And so from here, we can now just, because all of these are using just numerical values, we can go ahead and print all of our initial flow rates. And so we will print our flow rate into tank 1 initially. We'll print our flow rate between tanks 1 and 2 initially. And then we'll print our flow into tank 2 initially. And then we'll print the flow leaving tank 2 initially, which of course is the flow leaving our whole system. And so as you can see, we have the flow entering our first tank being equal to the flow leaving our first tank and entering the second tank. And then the total flow leaving our system here, Q2I, is equal to the sum of the flow entering our second tank from our first tank and from the inlet for that second tank. So these all make sense according to the initial steady state equations that we defined. And so from here, we want to find the flow rates as they change after a specific interval. And to do this, we can make use of our known initial flow rates, and we can use the sigmoid function to basically switch the flow rate at a specific time interval to something that we desire. And so we'll just define a function as qswitch, and it's going to take in a time, and then it's going to take in an initial value, and then it will take in a desired final value, and then we'll give it also a scale to use for the sigmoid function, and it will return to us eventually the flow, or the flow that's changed after a specific amount of time. So we'll give it the initial, or we'll give it a time interval, and then we'll give it our initial and final flows, and then we'll give it a time to make the switch at, and then we'll give it a scale. The scale is going to maintain or be the same for the first and second inlet flow switches. It's just going to be 1/1000th. And so for this, we're just going to return the sigmoid function, and then we need to change it a little bit so that it accurately reflects the point at which we want to, we need to change it so it algebraically represents a a value that we desire, which is this QF here. And so we need to return the JAX in, which is neural networks, sigmoid, and then we need to give it the time interval, so t minus t switch divided by the scale, and then we need to multiply it by the final flow minus the initial flow, and then add the initial flow. And then we will define two functions, one for each our inlet flow for our first tank and then the inlet flow for our second tank. And this will make use of this QSwitch function that we've defined, and basically we'll be able to give it a specific time, like for instance for QSwitch1 we will use 100 seconds. So we can switch the flow from being its initial value to 80% of the initial value. And we can do a similar process for the second flow. So our function for the inlet flow of our first tank with respect to time as a function of time. And we'll just go ahead and return the QSwitch, and we need to give it a time, and we'll give it this arbitrary time value here that we can eventually input. And then QI, the initial flow, is going to be the initial flow into tank 1. The final flow, we can just say, is 80% the initial flow into tank 1. The time that we're going to make the switch occur at is 100 seconds, and then we use a scale of 0.001. And then we'll do a similar thing for the flow going into our second tank. So return our QSwitch, and then we need to give it a time, and then we'll make use of the known initial inlet flow to tank 2, and then we want it to be 250% of that initial value, so 2.5 times the initial flow into tank 2. And then we want this to occur at 200 seconds, once again the same scale. And so now we have functions that will model the flow rates and how they change after a specific amount of time. And so from here, we can define the changing of height of the liquid in our tanks with respect to time. We can do this with another function. It's a function of time and height. And in this, we're going to eventually return the heights of our first and second tank, and we're going to return them in an array. And so we'll just define this so that our first tank's liquid height is going to be stored in the first column, and then the second column will be the height of the second tank's liquid. And then we need to eventually find the volume, because of course we know the changing of height is equal to the changing of volume divided by the cross-sectional area. And so we need to find equations for the cross-sectional area, and then we need to find equations for the changing of volume for each tank. Well, the changing of volumes for each tank can be found using these two equations, or these two functions that we've defined, and using the known flow rates between the first and second tank and leaving our second tank. So we can take these two equations here, except we can get rid of the I, because of course we are no longer using the initial values, and it's only using initial values of height, right? Well, in this function, we're assuming we've been given a height, and so we can find the flow rates across heights and across time between the two tanks and leaving the second tank. And then we can find the cross-sectional area of tank 1. We defined this equation in the previous video, it's just going to be equal to jacklumpy pi times 2 times R1, the radius of our first tank, times H1, the radius of our the height of the liquid in our first tank, minus H1 squared. And then cross-sectional area of our second tank is a very similar thing. It's using the same formula, except we use the values for our second tank. And then we can return dH dt. And of course, dH dt is dV dt divided by the cross-sectional areas. And so we want to return these dH dt's as arrays, and we'll return them as arrays across a time interval. And so we'll say return an array. And the first column is going to be the heights of our first tank's liquid. And so the changing of the volume of the liquid in our first tank is going to be equal to the flow coming into the tank minus the flow leaving the tank into the second tank divided by the cross-sectional area of our first tank. And then this second column will be the changing of heights of the second tank's liquid with respect to time. So that's going to be the volume, which is the changing of the volume, which is the inlet flow to tank 2 with respect to time, plus the flow between tanks 1 and 2, minus the flow leaving our second tank, divided by the cross-sectional area of our second tank. And from here, we can then go ahead and solve. We can find a result for this function here across a time interval. And so we'll make use of this solve IVP function, which is a solve initial value function. So we need to give it a function, we need to give it a time span, and then some initial values and a specific method to use to solve it. And so the function is, of course, dH dt, and the time span is going to be 0 to t final, which is, of course, 0 to 3,000 seconds. The initial values are going to be the initial values of the height, so h1i and h2i. Our method is going to be the Radal method. And then we'll use a dense output just so we can really get a glimpse of what's going on through the solving of our function of this dH dt across this time interval. And then we also want a Jacobian for dH dt, and we'll display the result. And so you can see we have a time interval going from 0 all the way to 3,000, that's in seconds. And then we have our array here, which is the changing of the heights. So the heights of our first tank is starting at 5, changing, and then the height of our second tank's liquid is starting from 3 and then changing, of course. So the important part from this is that we have this sol part here, and this sol is going to allow us to basically solve for values of dH dt across any time interval as long as we just call on it. So we can create a time interval and then plot it to show how the heights of our liquid are changing. So we'll create a time interval. It's called tplot because we're going to create a plot for this, and it's going to be a list of evenly spaced time instances. And so len space 0 to 3,000, which is t final, and say we want 3,000 evenly spaced points. Well, tf plus 1. And then we want to evaluate this sol here, this whole function that it gives us across a specific time interval. That time interval is t plot. So we can do so by doing res.sol t plot, and we will create a figure. And so basically what this has done is just we found our result here for dh dt across a time interval, and then we have used that result to use the equation that result gives us to solve for dh dt across a specific time interval. So from here we can solve for from here we can plot the dh dt across that time interval, and then also plot the flow rates entering our two tanks and how they change across that same time interval. Of course, that time interval is t plot. And so we can make a plot here, and we want the x-axis to be our time interval, and the y-axis is going to be our heights of our first tank across that time interval. So sol is 0. Sol is, of course, this function, and that 0 is just calling the first column of our array that it gives us. So that's the height of our first tank. And then this is column 1, row 1, column 1. And then we can do the same thing. Oh, well, this is not correct. So make subplots, rows 1, columns 1. And then fig dot add trace. And then there we go. So from here we can just add the same thing, except we are calling the second column of this array. So we're calling the heights of our second tank as they change with time. So H2. And then in column 2 we're going to, we do want 2 columns. In column 2 we're going to show how the flow rates entering each tank change with time. So we want the same x-axis as being the same time interval, and then our y instead is going to be qn1, so the flow entering our first tank. And of course it's a function of time, but we can use that time interval that we've already defined. So, and then we'll name it qn1, and then row 1, column 2. And then we'll do the same thing for the flow rate entering tank 2. And so you can see here, after 100 seconds, we have our flow rate into our first tank changing to 80% its original value. And then you can see how that affects the heights of the tanks, of the liquids in the tanks. And then you also have the flow rate entering tank 2 changing to 250% its original value after 200 seconds, and you can also see how both of these changes in flow rates affect the heights of the liquids in each tank here. Thank you for watching.